All right, so the learning targets for this set of notes is actually the same learning targets that would have been for our other parts of notes. I just forgot to put them. But explaining stoichiometry, which we learned in part 1, using balanced chemical equations to derive stoichiometric factors, aka mole ratios, which we've already learned. And the last one, performing stoichiometric calculations involving mass, moles, and solution molarity, aka volume. So we're hitting the last part of that today. So we're going to talk about volume to volume today. We're going to always start with our given in our upper left-hand corner. So our volume of given is going to go up here. We want to go from volume of given into moles of given. So does anyone remember what we needed to divide by in regards to volume? 22.4. So we're going to put 22.4 underneath. Oh, she left the meeting. Okay. In the middle is always our mole ratio. The middle is always going to be our mole ratio. Okay? So mole ratio is always in our center. That's going to be the coefficient of what we want over the coefficient of what we are given. Okay? Where do we get these from again? Do we remember? Where do coefficients come from?
Equation.
The equation. Okay, so they come from our equation. Lastly, we want to get to volume of our given, and we're just going to end up multiplying times 22.4 liters. So this one should be pretty easy for you. If you are a math mind, you might notice that the 22.4s cancel out. Do we see that? So when we're going from volume to volume, the 22.4s usually cancel out because we have one on top and one on bottom. So really, you're just multiplying times a mole ratio in reality with this one. But this is the actual setup for it, so you understand. And we're going to look at a practice problem. So our practice problem, how many liters of carbon dioxide are produced from 75 liters of carbon monoxide? So looking at this problem, our given is 75 liters of carbon monoxide. I'm also going to highlight carbon monoxide in my balanced chemical equation so that I have that kind of taken care of. I want liters of CO2, so this is my want. So I'm going to find CO2, and I'm going to also highlight that. Next, I'm going to just start to set up my train tracks. What always goes in the upper left corner of our train tracks?
Given.
Our given, and our given is 75 liters. So we're going to have 75 liters of CO. It's in liters, and I want to get rid of liters. So how do I get rid of liters? What do I put underneath that?
22.4.
Yes, we're going to divide by 22.4 liters. That way our units for liters cancels out. The middle is always my mole ratio. It's coefficient of what over what? Want over given. So what do we want? We want CO2. So what's the coefficient for CO2?
2.
So we have 2 CO2. We were given CO. What's the coefficient for CO? 2. Lastly, we want this in liters. So we're going to end up multiplying times 22.4 one last time. This one's kind of interesting. Do I technically even need a calculator? No. 22.4 and 22.4 cancel out. 2 and 2 cancel out. So what is actually my answer? 75 liters. Easy? So 75 liters of CO2. I don't know why that still wrote in yellow, so I'm sorry about that. But 75 liters of CO2 is our answer. That's a great to look at. Any questions on this? Is this pretty easy? Awesome. So I have a practice problem for you guys to try. On the very next page, how many liters of oxygen come from 75 liters of CO. So I'm going to give you guys a second to try this one, and then we will come back together and work on it. Alrighty, so with this one, our wanted was 75 liters of CO2. So you should have wrote 75 liters, sorry, not CO2, just CO, of CO. Next, you should have divided by 22.4. Our middle is our mole ratio. So we want oxygen, so we're going to put 1 mole of oxygen on top. We were given CO, so we're going to have 2 moles of CO down below. CO will cancel out. Liters also cancels out. The last step is to multiply times 22.4 liters. And the answer you guys should have ended up with is 37.5 liters of oxygen gas. Is that what we all got?
Yes.
Amazing. Spectacular. All right, so the next thing that we're going to learn is what's known as total stoichiometry. Okay, I do have a weird definition of it for you. And that is, given moles, molecules, grams, or liters of one substance, you can find any combination of those things of another substance. So for example, I could give you molecules of something and say, how many liters do I get of something else? Or if you have this many grams, how many molecules of this do you have? So that's total stoichiometry. It's a mixture of everything you've been learning so far. You already know how to do it, you just don't realize that. So the next slide is this flow chart, okay? I kind of want to explain this flow chart to you in a way that's going to make it make most sense. So the way that this flow chart's actually set up is it's exactly like a train track. Our given goes on the left side. If you are given moles, nothing goes underneath. But if you're given grams, liters, or molecules, we are dividing by those numbers and they go below.
Oh. Wait, so if we're dividing.
So if we're given grams, we're going to divide by the molar mass. So our grams are going to go up top, our molar mass is going to go down low. If we're given moles, nothing goes underneath because there's nothing that is divided, okay? Our mole ratio is always what goes in the middle. So that's always our mole ratio, okay? Always. And that's our coefficient of what we want over what we are given. Lastly, if we want grams, liters, or molecules, then we are multiplying by those numbers, and those multiplication factors go up top. If we want moles, then we're good. We're good. We don't need to do anything, because after this step, we don't need anything over there. Okay? I'm going to show you guys how to use this. You're going to like it, I promise. Okay? It's going to be nice for you. All right. Mechanically, are any of you guys familiar with how airbags actually work?
Sure.
You are?
No.
Has anyone ever wondered how, after I crash, how does my car know to inflate an airbag?
Isn't it a speedometer?
Not speedometer.
Probably good. Impact.
It's impact, but what causes it to bring in air? How does the air come in?
Outside.
It doesn't suck in air outside. It's actually a chemical reaction. So airbags actually have a solid, sodium nitrate, and after impact, they release it. It releases it, and it degrades into nitrogen gas and sodium solid. It's like a powder. The nitrogen gas is what fills up your airbag. It has to be almost perfect though, because what happens if you don't fill up your airbag enough? Is it gonna work?
No.
No, your head's gonna hit the steering wheel, right? Ouch. What happens if it fills up too much? Kills you. It's gonna blow up. It might be even worse than a car accident, okay? So there's actually chemistry that goes into the mechanics of an airbag. They need to know how big of a volume of gas do we need? So how much do I need to start with so that if we get in a car accident, the right amount of air is put in your airbag. And they actually do this using stoichiometry. So, if there's 100 grams of sodium nitride, how many liters of N2 gas is the airbag going to make? So, our given 100 grams of sodium nitride. Sodium nitride, I'm going to highlight here as well. What we want liters of N2. All right, so let's use our little flow chart to help us figure this out. So looking back at the previous page, our starting point, we had 100 grams. So are we starting with grams, liters, molecules, or moles? We're starting with grams. So it says if we're starting with grams, we're going to need to divide by the molar mass of our given. Do we all see that? Okay. So we're going to write our given, which is 100 grams up top. We need to find the molar mass of NaN3. Something a lot of you were kind of forgetting about molar mass. Molar mass is only for the compound. Molar mass does not care about the coefficient. Okay? We don't care about the coefficient with molar mass. We just care about the compound itself. So we have sodium and we have nitrogen and we have 3 nitrogens. Sodium is 22.99. Nitrogen is 14.01. Okay? When we add those up, we end up getting 65.01 grams per mole. So that's the molar mass of NaN3. Looking at our flow chart, what goes in the middle? Coefficient. What over what? Want over given. So what's my coefficient for my want? 3. So we have 3 moles of N2. What's the coefficient of my given? 2 moles of NaN3. NaN3 is going to cancel out. All right. What is this question? What unit is this question asking for? Liters. Okay. So we want liters. Right now I'm right here. I have moles. So if I want to get to liters, what do I need to do? We're going to multiply by 22.4. So that 22.4 is going to go up top right here. So in your calculator, you would have 100 grams times 3 times 22.4 up top. And then you're going to divide that by 65.01 times 2. So I believe I already have this typed into Desmos on my computer. I do. So 100 times 3 times 22.4 divided by 65.01 times 2 gives us an answer of 51.68. So our answer is going to be 51.68. What's my unit again? Liters and liters of N2. How was that? Do we like the flow chart? Is that helpful for us? Awesome. All right, so that's it for our notes for today. Those of you who are at home, I posted something on Classroom. It's a PDF called Total Stoichiometry Guided Practice. It's a worksheet that we're going to do a few questions on together today. So if you have access to it, could you open it up for me? And it is a PDF, so you might be able to open it in DocHub, or you can just write with a piece of paper. But you're going to want that, so get that open. And I gave it to you guys, right? So the worksheet looks something like this: guided practice, mixed stoichiometry. We're actually going to do questions 6 and 7 kind of together. So we're going to start with 6 and 7, okay? I already have on this worksheet filled in all of the balanced equations for you. So basically question 1, 3, 5, 8, they're all done for you. So you don't have to worry about those. let's look at question number 6. Question number 6 reads, how many grams of hydrogen will be produced when 5.1 moles of oxygen are produced? What is my given in that problem? 5.1 moles of oxygen. So we're going to find oxygen. It's right here. We're going to make sure that's highlighted. So that's my given. What do I want?
Hydrogen.
Specifically, what of hydrogen? Grams of hydrogen. So I want grams of hydrogen. All right, we are going to use our little our little flow chart to help us with this. We know that our given is going to go in the upper left-hand corner. So our 5.1 moles of oxygen, we know for starters is going to go here. But let's look at our flow chart. My starting point is moles. So right now I'm starting right here, moles. Do I need to put anything underneath of it?
No.
I sure don't. Okay. What comes next? What do I put in my next area? The mole ratio, which I get from my coefficients. So our mole ratio. I want hydrogen. So what am I going to write up top? 2 moles of hydrogen. What is going to go down below? 1. All right. The unit that I want is grams. So let's go back to our little flow chart. I want grams. So what do I need to do to get to grams? We're going to multiply by the molar mass of our wanted. So we're going to multiply times the molar mass of hydrogen. So we've got hydrogen, H2. H2 has 2 hydrogen. Hydrogen has a molar mass of 1.01. So that's going to equal 2.02 grams per mole. So up here, we're going to have 2.02 grams per mole. In our calculator, 5.1 times 2 times 2.02 divided by 1 is going to give us an answer of 20.6. Our unit's going to be grams, and it's grams of H2. How was that? Are we liking this flowchart still?
Yeah.
All right. I want you guys to give number 7 a try. So go ahead and try number 7 right now. All right. Let's go ahead and give this one a rip. So the question says, how many grams of hydrogen are required to produce 7.8 grams of oxygen? So our starting point is grams of oxygen. So we're going to write 7.8 grams of oxygen in our upper left-hand corner. You should have looked at your flow chart and realized, oh, I need to divide by the molar mass of oxygen. So you would have needed to calculate the molar mass of oxygen, and you should have came up with 32. Did we all do that?
Yep.
Amazing. Next, we have our mole ratio. So we want hydrogen. We're given oxygen. Our mole ratio should be 1 oxygen on bottom, 2 hydrogen up top. Did we get that as well?
Yes.
Amazing. Lastly, we wanted grams of hydrogen. So that means we're going to need to multiply times the molar mass of hydrogen, which is 2.02 grams per mole. And the answer that you should have ended up with is 0.98 grams of hydrogen. Is that what we got? 0.98 grams? Okay. So I know I've given you a lot of worksheets in the past week. Because of that, I'm not expecting you to do this entire worksheet. Okay? I'm going to give you 3 problems to do that are going to be due by the end of the hour tomorrow. So it's your main focus tomorrow is going to be working on this. Just 3 problems. I'm going to tell you what those 3 problems are. If you feel like doing the other problems, you get a DEEK dollar for each problem you complete. So you can get up to 3 DEEK dollars on this worksheet. Just to kind of give you guys a little incentive if you choose to do more than you need to. Do we like that idea?
Wait, what worksheet?
This worksheet,
Oh,
the guided practice.
Only get up to 3?
Yeah,
but she's giving us 3.
because I'm giving you 3 to do. And then that means that there's 3 left. So the ones that I want you to do, okay? The ones that you are required to do. Number 4. So basically number 2 is extra credit or DEEK dollars. Okay? Flipping your page over. I want you to do number 9 and number 14. So that means 13 and 11 are forms of extra credit if you choose to do them. Okay? So this rest of this guided practice will be due at the end of the hour tomorrow. Tomorrow you also will be getting your study guide for the quiz that includes practice problems to help you prepare for the quiz on Friday. Awesome.
Are the equations balanced on the guided practice?
Yes, all of the equations are balanced on this worksheet as well.